Let me remind you of where we stopped yesterday. I explained to you this phase diagram, the mechanical phase diagram, where we have here the on that scale we have the optomechanical coupling strength here in units of the natural mechanical resonance frequency, and that is the laser detuning from the cavity resonance. And on the red side of the cavity resonance we have stable dynamics, where if we have a strong enough coupling, and that means in particular that the cooperativity, which implicitly depends on temperature, where the cooperativity is larger than 1, we have this island of occupation number of the mechanical oscillator below 1. So that means cooling to the ground state of this macroscopic mechanical oscillator. Let me remind you also of the Hamiltonian, which is generating all that dynamics. So we have the energy of the cavity effectively given by the detuning of the laser from the cavity resonance. So that is the Hamiltonian in the rotating frame, rotating at the laser frequency, the mechanical energy, and that is this linear radiation pressure interaction. So that is this sort of X coupling, written here in creation and annihilation operators. Let me come back to that slide again, which explains the optomechanical ground state cooling in a level diagram, or in terms of this sort of sandbox Feynman diagrams. So the cooling effect itself is a completely classical phenomenon. So that as Pierre pointed out again yesterday, was discovered or predicted by Braginski in the 60s. And this level diagram and what I show you here really explains not only the cooling but also the quantum limitations. So this cooling of course has certain quantum limitations, and this can be understood on the basis of this level diagram, and it is the very same story as for two-level systems in ion traps via sideband cooling. So again, let's look at these diagrams here. The Hamiltonian, which we are using here, contains is the product of those two operators, A plus A dagger, B plus B dagger, and we can distinguish two classes of processes here. One where we have a quantum A generated and the quantum B annihilated. So that means a photon is generated and the phonon is annihilated, or the inverse process. And the other class of processes is where we create a photon and a phonon at the same time. Remember that this linearized interaction is proportional to the laser amplitude. So at the same time we always have in principle a laser photon being annihilated at that point, and then we create some sort of sideband photon along with annihilating or creating a phonon. That is described by these diagrams. We're coming with a laser photon, and now we can suck up a phonon from the mechanical oscillator and create another photon at now a higher frequency, laser frequency plus omega m, so at the upper side. And that is called the Anti-Stokes scattering process, and in these processes here, described by these terms in the Hamiltonian, we take a laser photon and we release a phonon and generate at the same time a photon at the lower sideband frequency. And if we detune our laser from the cavity resonance by just this mechanical frequency omega m, then we actually enhance the Anti-Stokes scattering, because then this upper sideband photon which we create here by these processes will fit in the cavity. So these scattering processes will be enhanced because the density of modes in the cavity is just higher at that point. And the Stokes scattering will be suppressed. The Stokes scattering would heat our mechanical oscillator because we create a photon at that time in that process while we suck it up here. So the cooling process is enhanced in that configuration, the heating process is suppressed. So that's another point of view of why this system is cool. Alright, so that was a summary of the cooling process. Now what is happening on the other side of the cavity resonance? this is the first topic I would like to cover today. So if we drive the cavity on the upper side, and we know in principle the dynamics is unstable, and now on the basis of such a level diagram we can also understand why. So if we drive, say, on the first upper side band, then we would not cool, but we would heat the system. We would make the mechanical oscillator climb up these stairs. So that's just another picture of this anti-damping which the mechanical oscillator experiences if you drive the cavity on the blue side band, where actually these Stokes processes are enhanced. Now we have come in with a laser frequency above the cavity resonance, and we enhance now the processes where we generate a lower sideband photon and at the same time create a phonon by taking energy from the laser. That process described by these terms in the Hamiltonian should remind you, of course, of the well-known parametric down conversion processes in nonlinear optics, where we have a Chi2 crystal, we come in with some pump, which plays the role of the laser in our optomechanical system, and we come in with two optical modes, which now in the optomechanical context are a single optical mode and a mechanical mode. And in that down conversion process, we can generate actually entanglement between the two optical modes. So let me make a short digression about entanglement and two-mode squeezing in the optical context. So in a, again, very simple-minded picture, you can imagine the nonlinear dynamics going on in such a Chi2 crystal as just a unitary evolution with a Hamiltonian given by exactly these terms AB plus A dagger B dagger. We also have in our optomechanical interaction. And if we, in the Heisenberg picture, transform the amplitude or annihilation operators A and B of these two modes here under that unitary transformation, what comes out is this. So this is a sort of input-output relation which would maybe describe a scattering process of two pulses going in here, or this is what we would get out if we could pump this Chi2 crystal with a short pulse. Then we would generate this evolution for corresponding pulses in the signal and idler mode. And the smoking gun of such a down conversion dynamics is always that the annihilation operators are mixed with creation operators. So A out is A in plus some contribution of B dagger. And B out is a combination of B in plus A in dagger. So that is what is describing our down conversion dynamics, and keep that in mind. So what are the properties of such a state? So that description in the Heisenberg picture is completely equivalent to an analogous description which we can derive in the Schrödinger picture. So let's characterize those states. So if we take each of those modes separately and look at the number of excitations on average, then we would find just a very large mean number of excitations. We would actually find a thermal state if we look at each of those modes locally. But the overall state is pure. If we come in with vacuum, we undergo a unitary transformation. So the resulting state is of course pure, and it is given by this equal superposition of Fock states in each of those modes, given weighted with this coefficient tangent hyperbolic to the power n, depending on r, where r depends on this unitary transformation. In the limit of very large r, this state here, which is a two-mode squeeze state, approaches this EPR state, which is at the heart of this Gedanken experiment of Einstein, Podolsky, and Rosen on the ostensibly incompleteness of quantum mechanics. So these states approximate this ideal entangled EPR state, where each of those systems is in the same Fock states, or they're completely correlated in the Fock states, they're completely anti-correlated in position, they're completely correlated in momentum basis. For such an EPR state, if you look at this representation here in position and momentum basis, you see that the sum of the positions and the difference of the momenta take on sharp values. So the variances of these non-local observables, sum of momentum, relative, sum of positions, center of mass position, relative momentum, take on sharp values. For the real two-mode squeeze state, this squeezing here will not be perfect. So the values will not be really well defined, but they will have some finite variance, but still the variance is below 1, which is the limit for uncorrelated systems in the ground state. So the EPR variances are squeezed in such a state. And actually, that is a criterion for entanglement for any Gaussian state. Entangled means we have a state which is not the product state of these two systems, and obviously our two-mode squeeze states would be entangled states. In reality, we will have to deal with mixed states. Mixed states are entangled if we cannot write them as a convex combination of product states for each of those two systems. And there is a very handy criterion for deciding whether a Gaussian state is entangled or not. Such a mixed state is entangled if the EPR variance is falls below, actually that should be 2, falls below 2, the limit for uncorrelated ground states. So with a slight generalization, you can make this turn this into an if and only if that are the criteria developed by Duan and Simon in 2000. So if you want to decide whether a Gaussian state is squeezed, entangled or not, we can check the EPR variance. If you find them below 2, so 1 plus 1 for uncorrelated systems should be 2. If you find it below 2, we are happy and have an entangled state. Please.
So it's like if I was to draw a Venn diagram of squeezed states and entangled states for Gaussian states, will there be parts which are not intersecting?
You mean locally squeezed states? Or, I mean,
so
entangled states are always squeezed states,
okay,
but non-local squeezed states, because the squeezing refers to this sort of non-local observable sums of positions relative momentum.
So how is that related to this criterion we already use this spin squeezing criterion from Peter, Duan, and Goldman and others, where you have to say that you have to have a very high number squeezing plus a very high average of cosine phi.
So this refers to two bosonic modes, and the spin squeezing, of course, is for a collection of spins, and then you. The question there is, given a collection of two-level systems, and you make some statements about polarization of the collective spin and squeezing or variances of some transverse spin components, what can you say about the multipartite entanglement within this ensemble? And so this is sort of a little bit different, because here we are not talking about collections of spins, we're talking about two bosonic modes. Of course, we can embed the bosonic mode in our spin, and then we can apply that. And then we can apply that, and this criterion would converge into what you know for a fully polarized state. And for a non-fully polarized state, it would look a little bit different. But it would make a statement about two collective spins, each carrying one bosonic mode in first element. All right, so remember the EPR variance criteria.
Can you also make a criteria, like in the spin squeezing, you make a criteria of how large is your part of the density matrix which cannot be decomposed anymore? Can you make something like that here too? That you can say, okay, but in the beginning this is good that you have some EPR. But the question is that, if you have something like in the bosonic mode an average of 1,000 photons, if you write down the density matrix, can you give a criteria that you say my density matrix has to have blocks that are at least 100 or 20 or 2 or 3 or 4? Because for example, if the blocks are 2 by 2, which I cannot separate, it's enough. Yes. But spin squeezing can give you something like a lower limit of the minimum size of the non-separable part of the density.
I mean, this refers to Gaussian states, and they are sort of full rank anyway.
But can you then talk in terms of entropy, for example, if not in terms of density matrices? Like, can you relate squeezing and entanglement for these bosonic states in terms of entropy?
Yeah, I'm not sure, probably. I mean, of course the entropy enters here because implicitly in this thing you have the mean number of excitations in there, and this can be related to entropy. Not sure. All right. So that smells a little bit like we can generate optomechanical entanglement between the optical field and this mechanical mode because we have the right terms in the Hamiltonian. We can try maybe to check this EPR variance. But the problem is, of course, that if we want to switch on this entangling interaction, we have to drive the system on the upper sideband, and the dynamics is unstable. So we cannot just shine our laser and generate a nice entangled state. It's unstable dynamics, so the system will just explode. We will lose lock in the cavity or something else bad will happen. But in principle, we can still do that, but not in CW operation, but we can drive the system for a short while. So remember that our oscillator here fulfills this effective equation of motion with an optically induced damping, and this damping will be at the upper sideband effectively negative. So we will have this unstable dynamics, but we can drive the system in the spirit of a pulse entanglement, of a scattering again. So we come in with the short pulse, whose central frequency lies at the upper sideband, plus omega m, and we reflect it off the optomechanical cavity, and we solve those effective equations of motion we have derived in that scattering scenario. So we solve the input-output relations for the reflected pulse and the oscillator after the interaction, depending on the input. Now, we want to do that under certain restrictions. Firstly, as I said, the pulse should have a central frequency at the upper sideband because we want to really enhance this Stokes scattering events. We cannot take a very long pulse here, so the duration of this pulse should be short on the time scale of the thermal decoherence rate of the mechanical oscillator. And I explained to you that the thermal decoherence rate of the mechanical oscillator is its intrinsic line width. In the generic example, a hertz times the number of phonons in thermal equilibrium, which is maybe 10 to the 5 or 6 in our generic example. So that is a megahertz rate. And the megahertz rate times our pulse length should be smaller than 1. So that sets the scale of the pulse we are allowed to use. If we take longer pulses, we will not see coherent quantum dynamics because our mechanical oscillator will just decohere. We want to be in the resolved sideband limit, meaning that the cavity line width should be smaller than the mechanical frequency because we really want to select one of these processes, the Stokes scattering, and we don't want to see the Anti-Stokes scattering, and this suppression is given by this sideband resolution parameter. And we also want to be in the limit of a weak coupling where the optomechanical coupling is smaller than the cavity line width in order to avoid that the cavity mode, the intracavity mode actually takes part of the game. So we want to generate entanglement or correlations between the mirror and the outside field, the pulse being reflected of the cavity.
So if the last criterion was reversed, you would generate entanglement between the mirror and cavity?
Yeah, one can still treat the situation and things will be more complicated, but that is the cleaner situation. So let's think about that first. So we can solve these input-output relations, and what we find just from integrating the dynamics is that the pulse which is generated here, and this pulse contains now the sideband photons entangled with the mechanical oscillator. This pulse has a particular temporal profile, which is this exponential envelope, and the exponential is given by g squared optomechanical coupling squared over cavity line width coupling. And for the operators of the mechanical oscillator and this pulse before the interaction and after the interaction, we will find these input-output relations. And remember now, the form of two-mode squeezing input-output relations. The amplitude operator, annihilation operator for this pulse is the incoming pulse plus some contribution of B dagger. And B out is B in plus some contribution of A dagger, and the coefficient scale like e to the r, not like sine hyperbolic, cosine hyperbolic, like in the real two-mode squeezing interaction, but in the limit of large r, that doesn't make a difference. And this r, the squeezing parameter in this game here, is given by g squared over kappa times the pulse length tau. And this state here, these input-output relations approximate for sufficiently large r very well the two-mode squeeze, a very clean one actually. Now, in contrast to what we have in the standard case in optics, the oscillator initially will maybe not be in its ground state. We can prepare it in the ground state by doing this sideband cooling, but possibly it's a little bit thermal. So the question is, what does this imply for the entanglement which we possibly create here? So we can take these input-output relations and just evaluate our EPR variance, which will be the criterion for entanglement, and take as an initial state the thermal state of the mechanical oscillator. And this is what I did here. So what you find is that the EPR variance essentially is proportional to the number, the initial number of mean thermal phonons in the mechanical oscillator times e to the minus r. So if you have sufficiently large r, you will go below this bound for the separable states and be able to verify that you generate an entangled state. And that equation means that in order to generate this entangled state, we need an r which is larger than some critical r naught, which scales only logarithmically with the number of phonons. So the logarithmically with temperature. That's very handy. So even for a pretty large number of initial thermal phonons, we need only a rather small value for R. So that raises, of course, the question how large this R can actually be. Remember that the pulse length should be smaller than the inverse thermal decoherence rate of the mechanical oscillator, and our R turned out to be g squared times tau over kappa. And that sets now an upper limit for this R, and this upper limit is g squared over kappa times gamma plus R, and this is nothing else than the cooperativity. So it pops up again. If you have an optomechanical system with a large cooperativity, larger than 1 or so, we already can tolerate a number of 10, 20 initial thermal phonons.
But then there's also an bar in the cooperativity.
Yes, yeah, temperature is there.
There, yes. So basically this logarithmic scaling goes away for an instrumentalist.
Okay,
because what you have control is g squared over kappa gamma. Yeah? This is what you really can control, and n bar is your temperature. Yeah? So basically you have, now this R scales logarithmically. So basically your advantage goes away, your logarithmic advantage goes away.
Okay, but the conclusion of that reasoning is, in any case, that if you have a cooperativity larger than 1, you're in business.
But then you're in business for n bar equals to 1. If they cooperate, then I can put in there for my g squared over kappa gamma without the n bar. With the g squared over kappa gamma, that's the thing I have experimental control of.
Yeah. I agree.
So if you want to get to 1,000 n bar, I need effective cooperativity I can engineer of the 10,000.
Okay, so but let's assume we have a sufficient cooperativity which allows us to generate an entangled state. So how would we verify it? No, we would need to measure the EPR variance. The light pulse which is coming out, being entangled with the mechanical oscillator, we can measure that. We can perform homodyne detection of that. So we can measure phase and amplitude quadratures. But we would also have to measure the mechanical oscillator, which is difficult because the only way we can look at it is by shining light and measuring light. But we can actually shoot now a second pulse, which is has a central frequency at the lower sideband. So we actually do this cooling dynamics, but not in CW operation, but we integrate again the equations of motion for a short time. And what that does is a state swap in the sense of this, the flip-flop interaction we already heard for the spins, but now it's for two bosonic modes, but still you can do a perfect state swap if you shine a short pulse at the lower sideband and solve the input-output relations. And what you find, for example, for the pulse running out of that system is that A out is just proportional to B in. And that means in the Schrödinger picture you swap the quantum states of the systems. So we can shoot the first pulse, measure the first pulse, then shoot the readout pulse, swap the mechanical state to light, and measure the second pulse. Actually, this swap operation has been shown by the Konrad-Lehnert group in 2013, and now we can combine that and perform the following protocol. We pre-cool the mechanical oscillator on the sideband, we shoot the first pulse, an entangled pulse, a second pulse, the readout pulse, and in the network scenario that would be the mechanical oscillator. The first pulse is entangled with the mechanical oscillator in the first step, and in the second step the mechanical oscillator state is swapped to light, and then we perform homodyne detection on the two pulses and correlate them to measure the EPR variance. And this was done by Konrad-Lehnert, again, with this electromechanical system I showed to you yesterday. So that is this mechanically compliant capacitor here being integrated in such an LC circuit. We have a transmission line. We can drive that system on particular sidebands, upper, lower sidebands, etc. And with the JDA, we can do phase-sensitive detection of the pulses generated here. And this is the data. So the first entangling pulse generates this temporal pulse here. The readout pulse has the opposite temporal shape, and by doing the right measurements, we can measure the EPR variance for various coupling strengths. So this is essentially G squared over kappa on that scale. That is proportional to the cooperativity. And above a certain level, we drop below this limit of uncorrelated states, which in that scaling is given by 1. So that generates actually an entangled and verifies an entangled state of the mechanical oscillator and the microwave pulse.
At which n bar do they start? Because there the cooperativity is given again without n bar.
Yes, because they do pre-cooling, the n bar is really close to 0.
Okay.
It's small. But in these systems, cooperativities of 1000 are actually possible. In the optical systems, cooperativities below 10 are difficult. But in the electromechanicals, they can go high. All right, so just to wrap that up, what does it mean? We generate a state, an almost pure quantum state, which is just implied by the small EPR variance here. I mean, it's not, it's squeezed by 1 pp, okay? But still, you wouldn't be able to do that with a very thermal state. A close to pure EPR state of this mechanical oscillator, this capacitor here with the traveling pulse being correlated in Fock states. Of course, that can be used now as a resource, because this is an entangled state for quantum information protocols. That is one of these examples where we create entanglement between a traveling carrier of quantum information and a stationary system. Like we heard today already with nitrogen vacancy sensors and photons. So that is another example of such a state. If we perform measurements on the pulse here, we can engineer the state of the mechanical oscillator. So one immediate thing, the pulse, if we detect one photon, we would project the mechanical oscillator into a phonon. And actually, that is, I mean, counting photons in the microwave world is not so easy, but it's possible. You can feed that transmission line into a second cavity containing a qubit, a Josephson junction qubit, and use the qubit as a single photon counter in the right way. So we're actually thinking about these things. Tobias Kittelberg and Nicolas Gissin have a similar proposal for optical systems, where the photon counting is easier, but it's harder because you would have to count the sideband photons. You don't want to count your carrier photons, and that means you have to filter your sidebands from your carrier, which is difficult in the optical domain. Easier in the microwave. So there are pros and cons. And actually, we have ideas to ultimately violate Bell inequality with these contained states and photon counting. So that would violate Bell inequality involving a mechanical oscillator. That would be nice. All right. So that is the entanglement of mechanical oscillators in light. And I remind you that this experiment, as well as the ground state cooling experiments, all essentially require in the right domain a cooperativity larger than 1. So that's really the benchmark. And this regime is something which really opened up in the last 2-3 years. And when you enter that, you can do quantum mechanics. So this is why these experiments are getting very exciting. So yesterday there was a question: what happens if we drive continuously on the upper sideband? Do there exist limit cycles? And I decided to add, I think 2 or 3 slides on that, through only in the classical context. So I will be very, very brief here. In order to describe what would happen if our entangling pulse would not be short, but just stay on forever, we are not allowed to use this linearized interaction anymore, because our system is unstable, so our linearization will break down at the moment, so we have to go back one step and look at the nonlinear dynamics. The nonlinear dynamics would be described by that nonlinear interaction Hamiltonian I derived yesterday. You can look at the nonlinear quantum equations of motion for A and B as well, which now are not linear anymore, because on the left-hand side you will have products, you will have quadratic terms, B and A, and here A dagger A, so you cannot solve that analytically. It's impossible. Or if you can't have it. But we don't want to solve the quantum equations of motion. We want to solve, in order to get a clue of what happens, the classical nonlinear dynamics, which we get just by replacing A and B by alpha and beta. So we get 2 nonlinear classical equations of motion for the complex amplitude of the cavity and the complex amplitude of the mechanical oscillator, now without noise, because we're looking at deterministic nonlinear classical dynamics. But let's take the same approach as we took yesterday. Let's integrate the equation of motion for the cavity and plug it in for the mechanical oscillator. Again, we assume that the mechanical oscillator oscillates. So we go to a slowly varying amplitude, B tilde, where we take out the fast oscillation with frequency omega m. We plug that in here. We get the equation of motion for the complex amplitude of the cavity and solve it. Now that is a differential equation with a harmonic coefficient here. So what we should use is a Floquet series as a solution. So the amplitude of the cavity will be a sum over sideband frequencies, multiples of the sideband frequency omega n, with partial amplitudes alpha n, which look complicated, but essentially depend on the amplitude of the mechanical oscillator via a Bessel function. So Bessel functions oscillate. I show you here the first few. You know these things. And this amplitude here, we plug now in the equation of motion for the mechanical oscillator. And what we have to evaluate here is sort of the mean number of photons in the cavity. So if we take this calculate alpha squared from that expression, we of course get a double sum. It looks very complicated. But what we are interested in is only the resonant component of that force, the resonant component of the mechanical oscillator at frequency omega m. So we pick out from that double sum only those components which oscillate like omega m. And then there will be many, many off-resonant contributions.
So you call the one that doesn't oscillate off-resonant?
Pardon?
The A alpha n star alpha n doesn't oscillate at all, but you ignore that as well. Right?
Yes, I ignore that as well because that's like a DC force. I mean, this will cost on DC displacement, that's trivial.
Okay.
It's also off-resonant in that sense. Yeah?
Okay. Yeah.
So the only significant force is the one which oscillates in phase with the oscillator. So we plug that in here, and again we can formally regroup this resonant component of the force in this first term here, and look at it as an optical shift of the damping and an optical shift of the mechanical frequency. But now these shifts depend implicitly on the amplitude itself. And that is something which causes possibly limit cycles, because if we now look at this optical damping on the scale of the intrinsic damping gamma n, then at the upper sideband of the cavity, or for blue detuning, actually, this optical damping will be large and negative for small amplitudes. That is our instability. That will make the amplitude blow up. And if the amplitude grows, the damping actually goes down, and at some point it gets positive. So we will be damped back to that point. Yeah? So there is an attractor in phase space. So that should be X and P here. And if we start here in a classical picture at the point here, it will be amplified because we are unstable, and at some point we run to that circle here, which is determined by the crossing of the optical damping or this effective damping with zero. So that is the limit cycle. Here you see this landscape of the optical damping versus detuning and our coupling strength. So that is similar to the phase-space diagram we had before, but before we referred only to small amplitudes, so that is essentially this cut here. But now we see that this optical damping is actually a very nonlinear function of the mechanical amplitude, and is negative on that side of the resonance, positive on that side of the resonance, and we would have here a bunch of limit cycles for a range of detunings. So that is what is happening, and it's actually very easy and generic to see that in the experiment. And one can also develop a quantum theory around these points here, and you can see that these limit cycles can have sub-Poissonian phonon statistics as well. Oskar Benker has a recent paper on the archive where he actually investigated the phonon statistics by photon counting of a mechanical oscillator in such a limit cycle. All right. That concludes the discussion of the optomechanical entanglement and the limit cycles on the upper sideband, and I would like to go now over to the position sensing. So how much time do I have for this? I don't know when I started actually.
We have about 20 minutes.
20 minutes. Oh, wonderful. So there is one spot left which I would like to discuss about optomechanics before finally turning to hybrid systems. And this is the resonant driving, which is the generic position for force or position sensing. So again, taking the linear equations of motion, which we derived yesterday, we have this detuning here, and now let's set that detuning to 0. If we set the detuning to 0, then that is used for position sensing, because imagine now that in addition to our thermal force, we have some other force acting here. That could be gravitational wave, or that could be some sort of force which causes spontaneous wave function collapse, or some hypothetical force generating macro-realistic dynamics at a certain length or mass scales. So something we would like to detect. That force is acting on the mechanical oscillator, and the momentum transferred to the oscillator will feed into the position, and the position is now something which we read out in our cavity field, because that changes the phase of the cavity. And the phase of the cavity we can measure by doing phase-sensitive detection here at the output of that cavity. So if we want to know how sensitive our sensor would be, our optomechanical sensor for that force would be, we should count and look at all the additional noise terms which enter that signal. So if we measure the phase quadrature of the output field of the cavity, we would certainly find some initial phase noise that is independent of the optomechanical coupling. So that is of order 0 in the optomechanical coupling G. We would find in first order G a contribution of our force, which we would like to detect, of first order, because here at this point we feed the mechanical quadrature into the optical quadrature with strength G. We would have a competing contribution by the thermal noise, which is also fed through the same way as our signal. And on top of that, we would have a G² contribution, which is amplitude noise of our laser, which we use to measure actually. So this amplitude noise fulfills an equation of motion which is independent of the mechanical oscillator, because we are on resonance, so that doesn't see the mechanical oscillator at all. The oscillator just changes the phase if we are driving on resonance. So this amplitude noise will just represent another force acting on our mechanical oscillator, and that force has a strength which is itself given by G, and that force we again feed through to the phase quadrature of the cavity, and now we have 2 orders in G. So that is the balance of the contributions which we have to expect here. So along with the signal, we will have phase noise, we will have thermal noise, and we will have amplitude noise, scaling with 0th power in G, 1st power in G, 2nd power in G. We can solve these linear equations easily in Fourier space, so let's do that. The phase quadrature in frequency space at a particular site and frequency from our laser would be initial phase noise, signal and thermal noise with order G, and amplitude noise with order G². And in addition, we will find the mechanical susceptibility given by this expression here as a prefactor for all those noise forces driving our mechanical oscillator. Now, that is something we can measure. That is the thing we would like to know. So if we get a number for this quantity, how would we infer the magnitude of that sought for quantity? Well, we can just scale whatever we measure here by this known prefactor and use what we get out as an estimate for our force. So if we do that, we would find our signal, and on top of that, phase noise, thermal noise, amplitude noise. Now in that scale version, scaling like 1 over G, independent of G, proportional to G. If we now ask for how sensitive this sensor is for a given signal, then we should compare it to the magnitude of all those additional noise forces, because we will not be able to detect any signal which is smaller than whatever is next to it here. And the largeness of these noise forces we can characterize by the variance or the noise spectral density at a particular frequency. And this is what I write here. So the noise spectral density of added noise, and that sets the level of sensitivity which we can have here, is the phase noise spectral density weighted by 1 over G². Now we are in the variance, everything is squared here. The inverse of the mechanical susceptibility, spectral density of noise force, of thermal noise, and spectral density of amplitude noise weighted with G². And now let's make again a very simplified consideration and assume that all those noise forces are white. We can assume that phase and amplitude noise are white vacuum noise, so let's give that a level of 1. And the thermal noise would be given by gamma n bar for the mechanical oscillator. And then there's noise spectral density, which sets the scale of the sensitivity of our optomechanical force sensor, would be given by this expression. Let's plot that as a function of g squared, and g squared is amplitude squared. Intracavity amplitude, that means power. Yeah? So at first, for small powers, we get higher sensitivity. Small noise spectral density means high sensitivity. Yeah? So first, we crank up power, and what we do is just we suppress the phase noise relative to our signal. At some point, we would see the thermal noise floor of our mechanical oscillator, and if we crank up power even further, we would lose sensitivity again, because we will have so-called back action noise. The amplitude noise fed through to the phase noise. Let's consider this point here, which is relevant if we actually don't have thermal noise. So let's assume we are able to switch off thermal noise, so that just means take a temperature which lies below that crossing here. Then we have something which is independent of temperature and really makes a statement just about the mechanism of our force sensor. And this point here, the minimal sensitivity, is called the standard quantum limit of continuous measurements. So beware, the notion of standard quantum limit is very much non-standard. So in different communities, standard quantum limit means different things. So if we talk about magnetometry, then the standard quantum limit is just given by the projection noise of atoms, or also in atomic clocks, and that is like scaling like 1 to the square root of n. People are doing QND measurements there, they don't see back action noise. And what I'm talking about here is a measurement where we measure continuously a mechanical oscillator, and where we will see the effect of our measurement at some point spoiling the sensitivity of our measurement. So, standard quantum limit of continuous position or force measurement. And we can determine that minimum, of course, by minimizing this expression with respect to g, and what we find is that it's the inverse of the susceptibility that is called the standard quantum limit at a particular frequency, cycling frequency. Alright, so if we plot that standard quantum limit, we will see that we will have highest sensitivity on resonance, we will have this free, so-called free mass limit far above mechanical resonance. That is what is relevant in the gravitational wave detection community, where the mechanical frequencies of these hung mirrors is in the Hertz regime, and the relevant detection bandwidth is in the audio band. So they're up here, where the mechanical oscillator actually behaves like a free mass. So this standard quantum limit, although I derived it here for the Fabry-Perot cavity, applies just as well to something like LIGO, because in LIGO this is not just a Michelson interferometer, this is actually a very complicated array of cavities, because people use arm-length cavities, and more importantly, not shown here actually, is a signal recycling mirror. So you have a lot of cavities in here, and there is something called the scaling law in that community due to Yang Chen, which states that for a tuned signal recycled Michelson interferometer like LIGO, the sensitivity limitations, quantum limitations, can be understood on the basis of the Fabry-Perot cavity. So the same logic I explained to you applies to these systems and sets the ultimate limit here, and current detectors don't reach that sensitivity yet, but next generation is planned, set up to reach the standard quantum limit. So that is sensitivity curve versus frequency. I don't want to go into detail on all that lines here, but note that the violet curve here is quantum noise. So that means we reach the standard quantum limit at these frequencies. And the total noise should be limited by quantum noise, so should reach the standard quantum limit over a broad range of frequencies in the next generation of detectors. Which is remarkable because that says we sense the motion of this kilogram scale mirrors at the quantum limit. You cannot make more precise measurements, not without little tricks. All right, so I think you mentioned that abstract yesterday,
yeah.
so I show that abstract because this is the way you should write an abstract. Case treats the question whether interferometers being developed now for gravitational wave detection measurements are limited by radiation pressure fluctuations or not. So he says there has been a controversy whether quantum mechanical radiation pressure fluctuations disturb this measurement. This letter resolves the controversy. They do. This is the spirit. No? We're not always able to write it in such a clear way, but we should always attempt to do so.
It depends if the paper has a clear message.
if it doesn't think about
Whether you should write that paper.
All right.
By the way, it's a great paper.
It's a great paper, yes, so really, yeah, it's really classic. And it's from 1980s. And he says, well, there is this limitation, and now, 35 years later, we are almost there. Okay. There is another interesting point in that sensitivity diagram here. So I was talking about the standard quantum limit here, but we can also look at this point here where back action noise comes up above thermal noise. So let's look at those two contributions. I'm looking now at the situation where back action noise is larger than thermal noise, and you will see that it's just the large cooperativity limit. So in any system which has a cooperativity larger than 1, you actually, if you use it as a position sensor, you're in the situation where back action noise is stronger than thermal noise. That means your measurement disturbs the system more than its thermal environment. It's a very remarkable situation. Yeah? And the dynamics of the mechanical oscillator will then be really driven dominantly by optical vacuum fluctuations. But this is, the optical field is a special environment because this is something we can measure. Yeah? Whereas the phonons coupled, the phonon modes in the environment of the mechanical oscillator driving that system, we cannot measure. That is a true environment. We don't have access to that. But the fluctuations of the electromagnetic field driving the mechanical oscillator here, dominantly being the dominant, representing the dominant environment, is not really an environment. This is something we can do very precise and efficient measurements on. So that's a very interesting regime now, also from the perspective of performing measurements and learning about the mechanical oscillator. I can tell you that the conditional state of the mechanical oscillator in that regime, conditioned on the detection of light, will be a pure quantum state. Because, roughly speaking, we generate entanglement here, and if we do a projective measurement of light, we will project the oscillator in again, larger, C larger than 1. And that has been observed in the group of Cindy Riegel, Boulder, driving the optomechanical system on resonance, taking the spectra of the position sensing, and they saw that if they crank up power, the sensitivity goes up again. That is something the gravitational wave community was attempting to reach for a long time, and now somebody from the AMO community comes and just does it. But they will do it, I guess, with the large mirrors in boxes. With the micromechanical systems, we are not reaching the standard quantum limit. So we reach that point where we have back-action noise above thermal noise, but we cannot reach yet the point where thermal noise is below the standard quantum limit. So that is not possible yet with these systems. But still, with the large gravitational wave detection setups, they're supposed to reach that limit, and also the micromechanical systems will do that at some point. And the next interesting question is, of course, how can we surpass the standard quantum limit? And I think that should be topic of the next lecture. And actually, there I will present one strategy where I use a hybrid system. I use atoms to go below the standard quantum limit. All right, I'm happy to take questions.
Thank you.
Yeah, so I just had a question about the limit cycle behavior and how it affects the degree of squeezing. Does it map the pulse?
The degree of EPR squeezing?
Yes, the degree of EPR.
Well, in the limit cycles, so the rough answer is I don't know, but I don't expect there is entanglement anymore in the developed limit cycle. I mean, what happens if we think about the Leonard experiment in that diagram? We prepare the mechanical oscillator in the ground state, so we have a Gaussian blob here sitting, and then we drive the system on the other side. And if you look at the system locally, it just gets hot, so this thing blows up. Yeah, we blow up the initial uncertainty. Of course, it's a very controlled blow up because we feed in light noise and we blow it up correlated with light. And if we would not stop after a short time and forget about thermal decoherence for the moment, of course that changes, that would destroy everything. But let's just think about coherent dynamics. Then we would blow up this ball further and further, and at that point here, the dynamics changes, and we would be stuck to that line here, and actually the population inside here would disappear, and we would go to a ring, which ideally is correlated with photons leaving the cavity in phase. So you can look at it as maybe even a coherent state being randomly distributed on that ring, but in phase completely correlated with light leaving the cavity. So it would be some weird entangled state. But I don't think it's really feasible to do that because before you arrive here, temperature will kill you. So you will be localized in phase space before you reach the limit cycle.
But would the width of that ring be actually less than, like, that state is a number squeeze state, right?
It can be a number squeeze state,
But
yes. And this is
to
exactly
have
this.
number squeeze
Yeah.
state.
And generically, it will be a Poissonian statistic, so you will have really a coherent state on the ring or a thermal state. But if you're non-linear enough and your G naught single photon coupling is large enough, that will be a number squeeze state. Any further questions? Everybody's hungry.
One comment regarding, since discussing papers, one of Paul Caves and Wittgenstein, the EPR paper by Einstein, I think is cited paper. Einstein's most cited paper.
Einstein's most cited paper?
Yes.
On what?
You know, all 5 papers, but the EPR paper.
I think EPR
The one
paper.
in
It was ignored for a long time, and now it's...
Yeah, and also I think that the stuff he did in 1905 has become so much textbook by now.
Yeah.
And there are so many physicists, more physicists now than when this stuff became textbook. I still think that his relativity work was not bad.
Good.
Touche.
Thank you.